Hello, good afternoon. Hola. My name is Arvind Hosagrahara. It's a complicated last name, just Arvind at MathWorks. I'm here to talk about engineering analytics for predictive health applications. I'm a principal engineer with the MathWorks. I'm based out of the Bay Area in California. Very happy to be here. And I lead a small team of engineers that focuses on integrating our products with the rest of the open source platforms and frameworks. And today we'll be focusing on streaming analytics and how to build a full system to do engineering analytics at scale. As an agenda, a typical data analytics workflow starts with accessing and exploring data, pre-processing, developing predictive models, integrating and taking it out to production, or scaling it up to production so that you can visualize results and provide actionable insights to users and business users of your system. And to do this, we work with a lot of customers. Most of it we can't really discuss in a public forum. But what I can talk about is a system that we stood up to generate our own data set. What we did is we picked up a bunch of our colleagues drive cars. We took a small piece of electronics and plugged it into the OBD, which is the onboard diagnostic port of these cars. These devices talk to cell phones, and cell phones talk up to our servers in the cloud. A continuous stream of information, once per second, data coming from engine sensors, fused with sensor readings from the cell phone itself. That includes things like GPS, things like acceleration, and in our case, we actually were capturing video too. So pretty much a big data set that built up very quickly, and we have over 1,600 trips from our colleagues operating the cars at scale. And we'd like to use this data to assess the health of a fleet, to be able to build predictive models and analyze driving habits of my colleagues or the participants. And this is a system which started spitting out data. What you're seeing here is a visualization of events in the Bay Area, along with trips in the South Bay or near San Jose. Each color represents a different trip. This visualization shows our headquarters in Boston, cars coming in. The data begins to tell a story of where people park the cars and how they ingress and egress the headquarters. This is our offices in Detroit and in Novi. Some of this data is very interesting. I can assure you I was not driving my car through buildings, right? There is GPS signal degradation showing traces of drives through buildings. And for the large part, a rather large data set, every IoT problem is a big data problem in disguise as these little streams of chirps of information build up. So some more data in the Midwest, both city driving and long distances across the Midwest. But to take a step back and talk about the architecture of a system, edge devices, in this case cars with a little piece of electronics, passing data across to a cloud-based system where we would ingest it through a secure gateway, pass it through Apache Kafka. Apache Kafka gives us the scalability of a distributed queue that we can then take the data and push it to cold storage systems. We were using, since it was a cloud-based system, we were using S3. But it is possible to take the continuous stream of data and be able to run your analytics or predictive models on the data as it comes in. This is the streaming analytics part. Those analytics, there is a workflow for developing it, and I want to get through the slides quickly so that I can dive into a demo and show you exactly what it looks like. It's a pretty risky thing to do on stage, but I will do it. And finally, expose the results out to business decisions, to dashboards. You know, the previous speakers had a Kibana dashboard showing that kind of insight. But irrespective of which business BI tool you're using, ability to expose those results to your end users. So the first step is to clean up the incoming data. And before we start cleaning up the data, a little insight into the timestamp messages that were coming. We were ingesting data as JSON messages. You could see the ID of these cars, timestamps, and some of these KC and KFF are what are known as programmatic identifiers, or PIDs. And these PIDs contain engine sensor readings. In this particular case, fuel flow in grams per minute or grams per second, as well as engine speed and a bunch of engine sensor values. Accessing the sample of data, we could connect up to these storage systems, pull the data in for analysis. We could slice and dice the data. That becomes your serving layer. We could slice and dice the data on S3 by using products like Presto or AWS Athena, which is a hosted version of Presto, to bring forensic pieces of information into Matlab for the process of actually building the model. That workflow, being able to clean up, being able to create data structures that you can very quickly stack and scrub to ensure that you handle missing values is something that which I will be demonstrating shortly. And once we actually pre-process this data, it is possible to clean up, enrich it, and restructure it in ready for to prepare it for the modeling effort. There is a lot of research that shows that this is where the bulk of most data scientists' time go. So certainly, APIs to actually make this process a lot easier goes a very long way. Finally, we get into the process of actually building a predictive model. I got a short video here, and I'll go into a little bit more detail. But this is a predictive model that you can then stick up on a production system and run your development workflow. For example, everything that you need to do this can be found in Matlab: ability to label the events, ability to visualize the signals, ability to train the models, and validate and scale it upwards. This is the first part of the demo. This is a very short video here, but what I will do is at the end of this, try to do the whole workflow as a demonstration and show you what it will look like. In this particular case, I'm connecting up to one of the many domain-specific apps. We call it the classification learner, pulling in my data set, picking my events and my predictors, and I can specify what kind of validation I want. In this case, I picked a holdout validation. There are features for you to actually visualize your data set itself, giving you an idea of what kind of data you're dealing with. And the training can be done in parallel. And what I'm doing here is actually classifying my data as events that pertain to safe driving or hard braking or hard acceleration. Are my drivers going very fast out of traffic stoplights? Are they braking very hard and whatnot? It's possible to understand the performance of these models. You can take a catalog of these models, and it gives you a rough idea of how they're performing in terms of accuracy. The confusion matrix over here tells you how well it performs, and you can export that as into a variety of formats, including generating just MATLAB code from such a system. So the last step of this process would be integrated with a production system. In this case, we connect up that analytic model, the predictive model, to an Apache Kafka topic, so that as data appears in the real-time stream, we consume it batch at a time, perform our prediction, and store it, making it easier for you to query it later on. This workflow for developing is kind of unique because you can actually tie in the development tools to live streams of data as they come in, and I hope to demonstrate that in a bit. So, but before we talk about developing that analytic, a quick introduction to stream processing. Typically, with big data problems, there is the batch processing layer, which gives you access to historical data so that you can configure your resources, schedule and run jobs, take the output and report on it, do data exploration and report on it. This is the kind of workflow that is supported by products like Spark. The MATLAB code that you build works with these infrastructures. You can actually export and deploy a Spark job that you can take to a Spark cluster and scale out your computation across the batch load. But stream processing, on the other hand, applies the computation to an unbounded data set that is continuously produced. In this case, By connecting up to a messaging service, we actually apply stream analytics. There's a certain notion of maintaining state as newer information comes in. And finally, expose that through dashboards, through reporting, giving you near real-time decision support. And by saying near real-time, I'm very careful because you can actually run these analytics on the devices, on the cars themselves, giving you hard real-time. People in the embedded space understand what that means. But near real-time is near real-time decision support. So why stream processing? Typically, you can break up your analytics into three, depending on the amount of time it has been since the data has been gathered, into three sections. The first one being your big data processing on historical data. This is your batch job. And of course, you can actually take these analytic models, generate C++ code, compile it down to your device that's running in your car or in your medical device or in your producer. And that is done instantaneously on the edge. But today we'll be talking about pulling that data with providing both actionable and reactive insight into your data stream as it comes in. In this particular case, the challenges of why you require something like Apache Kafka become clear when you see the nature of the data that comes in through the system. You'll notice that multiple cars are talking to the system. In this particular case, I've got two cars that end with FD and FE, passing in data at different timestamps. I perform my compute, update my time-windowed results table, and process the next batch of data, where I go through, pick up my previous state, update my analytics, and update my time-windowed results table. This results table goes into a persistence layer. You can pick any persistence layer. We don't make any kind of databases, but you can certainly push it into a database to which you connect your business intelligence systems for visualization. In this particular case, the process of continuously taking this unbounded stream is what we define as stream analytics. So one part of this infrastructure uses a product that we make called Matlab Production Server. Very simply put, Matlab Production Server is to Matlab as Tomcat is to Java, right? It's an application server for Matlab code, allowing any Matlab algorithm to be put up as an HTTP or HTTPS-based service that will scale concurrently, that can be load balanced, and that can actually execute. And that is the endpoint to which we connect up Apache Kafka. You can also connect it up to other endpoints, like run your Matlab models behind your Tableau and your Spotfire and your Click dashboards, or your reporting layer, or connect it to databases so that you can actually execute user-defined functions inside databases powered by Matlab Compute. So it is an enterprise-class framework that is designed to run 24/7, and it runs on top of a freely available Matlab runtime. You can download this off our website, which is basically Matlab that is free to run, allowing you to scale very effectively. We provide a whole bunch of lightweight libraries in Python, C, C++, .NET. So depending on what the rest of your system looks like, you can get access to Matlab analytics from these contexts. And finally, there is a clientless or a RESTful JSON way of connecting. It's just a simple curl command will give you the ability to pass data across to Matlab-based compute. So if any of you used Matlab way back in your college days, this is a very different Matlab. This is the next generation of what it looks like. So the last part of this is that we connect up the production server to Kafka, pointing up a client to consume from the Kafka topic and feed it into Matlab analytics that's running on this server. Pretty much everything is driven via just simple configuration files, at which point you have the ability to develop these analytics, debug it, and understand how your streaming function works, and certainly pre-process your data, compute or predict events with our predictive model, and certainly count the events as they actually happen. So the last step of it is you take the results, you complete out your application by building out the rest of the front end. We put together a very simple sort of homebrew interface to show what this looks like. But if you had the skills to do that, you could certainly do that. Or most people use BI reporting tools like your Tableau, Click, Spotfire to do this. So with that, I'd like to dive into a demo. And I've got one more slide after that to just close it all up. This is where things get colorful. I'm going to be trying to do a live demo, and hopefully this thing has the network connectivity to do that. And if this doesn't work, at least you know it isn't a recording. So there's a system here that we spun up. We've spun it up on the cloud. And if you're sitting in front of your computer, you can actually connect to this, which is a system that will give you, let me see if I can figure out how to make this a little bigger. Yeah, which will give you insight into this fleet. To understand what we're doing here, it is possible to take a look at a summary of events as the streams come in. We colorize it by the magnitude of the event and classify all learning, all the predictions into aggressive acceleration, deceleration, braking, or safe events. The model that's behind this is not a very good model. It's showing that all our drivers are driving really aggressively braking or decelerating, which sounds about right for Bay Area traffic, but I suspect the model. The last bit over here is just how many events we have processed here. So if you wanted to go, I'm going to now put on my IT hat on and spin up a Kafka cluster and connect it up to a Matlab session. So to do that, the first thing I will do is actually connect up to an edge service that is running. This currently runs Apache Guacamole, giving me the ability to bring up Matlab. But at the same time, I'm going to bring up a couple of other services, such as my Kafka cluster. So the first step is to start Zookeeper. I'm not going to go into these technologies, but Zookeeper gives us a way of actually building up a service that Kafka connects to. It's done for resilience. On this, I'm going to now start up Kafka. And the last service over here involves us starting up the connector to our Matlab production server. Each of these services have their own configuration files, at which point we now are taking data and trying to push it to Matlab. In this particular case, if we go back to our system here, it is possible to pick up a service and put our analytics so that you can actually see the live stream of data. The development of this live stream of data would start with a whole variety of apps that we offer. In this particular case, I'm going to bring up the classification learner app. This allows people that understand the data but don't necessarily have don't have the software expertise or the machine learning expertise. It lowers the bar to get into machine learning. So in this case, I'm going to connect up to a forensic piece of data by picking up data that has come from S3, specifying what my response should be. These are the events that I'm trying to predict, and what kind of predictors that I would like to use. I can pick what kind of validation I'd like to use, either hold out a certain segment of my data, or perform cross-validation and start a training session. When I do this, it is possible for me to go to my showroom of models, and if necessary, pick all quick-to-train models, since I'm doing a demonstration here, visualize my data. In this case, I'll take a look at speed versus something like fuel flow. And asking it to train would connect up and bring up a training session in parallel across a whole cluster of machines and take these different catalog of models and train them in parallel and give me a sense of what kind of accuracy I would expect with my given data set. I'll make this a little wider so that you can see this. So a couple of tree bagging algorithms. There's a couple of k-means, nearest neighbor algorithms, different machine learning algorithms that you run in parallel. And it'll give you an idea of what these look like. You can study the performance of these by taking a look at the confusion matrix and selecting which of these models to understand exactly how it has classified and categorized my data. So in this case, it goes through multiple models. And when you're happy with the model that you like, you should be able to pick it up. Let's say, for example, we pick up a KNN and export this. This can be exported either as a binary model or a compact model without the training data, or you can even generate code, in which case you produce code that will actually perform the prediction. This code you can actually spin up as a service. And this particular tool over here spins up a single instance of what looks like a Matlab production server thread, where I specify my function that consumes the data from Kafka. I have an interface here for enabling cross-origin requests. And when I start this, what you start seeing here is a live stream of data coming in from Kafka, batched up, coming in one at a time, being fed out from Kafka. And as it processes this, it actually writes out into a database. And if you went to the web page, you can actually see the data begin to flow in real time. The one key differentiator or feature is that differentiating feature is that it is possible to go and add breakpoints to this. I can actually break on function entry. I'm actually debugging a live stream of data that's coming from Kafka. It will stop my code at a debug breakpoint, giving me the ability to step through my data or focus on the math itself by going to certain parts of my algorithm where I'm actually predicting. This is me inspecting the live stream of data. And if I wanted to, I could just take a look at the raw data itself. And take a look at what kind of predictions were done in this particular time frame. So as you can see, this is the raw data. But if I step this, what I do is perform a prediction of my current data and take each data point that I've got and classify it as either an OK driving event, a hard braking, or a hard acceleration event, giving me the ability for me to classify a live stream of data. The last part of this is if you went back to our web application, you should be able to see our fleet summary. In this case, I've got 154,000 events. But if I refresh this, this is near real-time insight. I should see that counter actually tick. I've done 154, 753 events, classifying it and updating my graphics or my BI graphics. This is what we are calling as near real-time insight into an operating stream of vehicles that is currently moving all over the world, right? We got data from as far as Pune to the Bay Area. So with that, I'd like to jump back to my slides and close up, leaving a few minutes for questions. Right? So as key takeaways, Matlab allows you to directly connect to your data so that you can quickly design and validate algorithms, gives you ability to deal with unbounded streams of information, allows you quick and fast design iterations and easy integration with the rest of your enterprise system, irrespective of which technology stack you're using. You spend your time understanding the data and designing the algorithms, which is a sort of write less and do more, if you may, by focusing on the data, focusing on the algorithms that you would like to apply and the insight that you would like to get. A set of resources over here. I'm sure this becomes available on the conference proceedings. But we do also have a booth here, booth number 8. Please do stop by if there's anything that we can do to help. With that, thank you for listening. We got about 4 minutes left if you have any questions. All right, so I'll be available here at the booth, so feel free to come and find me later too. So, thank you.